Hi, we now come to part 4 of mechanics, and we're going to look at force diagrams, and these can be used to represent all the forces which act on a body. Let's look at the first example, men on parachutes. Well, there are two forces acting upon each of the men. The first is the force of gravity acting downwards. The second is the force of air resistance acting upwards. In the right-hand example we have a moving car. We have a number of different forces acting upon the car. First of all, we have its weight, shown by the green arrow, and then opposing forces, which are the reaction forces which come up through the tyres, and they are shown by the blue arrows. The car has a driving force, shown by the yellow arrow, and there are two forces opposing motion. These are the air resistance, the purple arrow, and the friction between the tyres and the road surface, shown by the red arrows. Now, if you're drawing these types of diagrams, you have to remember that forces are a vector quantity. They have both magnitude and direction. So first of all, you need to use arrows which indicate the direction of the force, and secondly, you need to show that the length of the line is roughly equivalent to its magnitude. So if a body is not accelerating, then the forces that act upon it must be in equilibrium, they must be balanced. Let's say this was the case for the two parachute men shown on the right hand side. So overall there is no resultant force, they've stopped accelerating, they've reached terminal velocity. How would we represent these two forces? Well, first of all, they're acting in opposite directions, and the lengths of the line of both the force of gravity and the line representing the force of air resistance are the same length, to suggest that they are the same magnitude. It's often necessary to split the forces up into their horizontal and vertical components when you are doing calculations. Let's look at an example. We have a box, weight 60 newtons. It's being pulled in the direction shown by a force of 20 newtons. And there are two further forces acting on the box, F2 and F3. Now, if the forces are balanced, then the forces acting in the vertical direction must be equal to 0, and the forces acting in the horizontal direction must be equal to 0. So let's have a little look at the forces acting in the vertical direction. We've got a 60 Newton weight which is acting downwards. We have F3, which is also a vertical force acting upwards, and also acting upwards is a component of the 20 Newton force. So if we add all of those together, that's 60 minus F3 minus 20 sine of 30 degrees. They all should be equal to 0, so we can find the magnitude of the force F3, which is 50 newtons. If we look at the forces acting horizontally, well, we have just the horizontal component of the 20 Newton force, and that is being opposed by F2. So the horizontal component of the 20 Newton force is 20 cos of 30. So if we subtract that from F2, we must equal 0, and that results in the fact that F2 must be equal to 17.3 newtons. Let's look at another example. Let's say we have a box of weight 5 newtons. It's stationary or otherwise moving down the incline with a constant velocity. That means the forces are balanced again. You're asked to calculate the reaction force of the incline on the box and the friction force on the box. Well, the reaction force R must be equal and opposite to the component of the weight that's acting in the opposite direction. So that is W cos 30. We're told that the weight of the box is 5 newtons, it's 5 cos 30, so that's 4.33 newtons. Equally, the friction force must be equal and opposite to the component of weight acting down the slope. The component of the weight acting down the slope is 5 sine 30, and that comes out at 2.5 newtons, so that's got to be equal to the friction force. And that is the end of part 4.
Created using Powtoon.